Imagine an AI that can not only create stunning images from text, but also precisely edit them, change styles globally, or even enhance realism, all within a single, unified model. This is the grand vision for modern image generation. However, achieving this unification is incredibly challenging. Different capabilities often conflict, leading to performance degradation. Today, we're diving into DanceOPD, on-policy generative field distillation, a groundbreaking paper that tackles this very problem by teaching models to dance between different creative abilities. The core issue is capability interference. Think of it like this. If you train a model to generate images from text and then try to teach it to edit specific objects, the editing process might accidentally degrade its original text-to-image quality. Similarly, local edits, which preserve most of the image, can clash with global style changes that transform the entire scene. Existing methods often dilute specific supervision, leading to compromised solutions or requiring complex inference time tricks. The fundamental question is, how can a model effectively compose multiple generative capabilities without them stepping on each other's toes? DanceOPD introduces a powerful new perspective. It views each generative capability, whether it's text-to-image or a specific type of editing, as a velocity field in a shared generative state space. Imagine these fields as invisible forces guiding the image generation process. The goal is to train a single student model to learn from these diverse teacher velocity fields. This is done through a process called on-policy generative field distillation, where the student learns to imitate the expert's guidance on states it actually generates itself. DanceOPD addresses 3 key alignment challenges. First, target field ambiguity. Instead of mixing multiple teacher fields, it uses hard-routed sample-wise field matching. Each training sample is assigned to one specific teacher field, preserving its semantic identity. Second, state distribution mismatch. The student queries the teacher fields on states it generates itself during its own rollout, not on fixed, off-policy data. This ensures the student learns where it actually operates. Third, trajectory query correlation. To avoid redundant supervision from highly correlated states along a trajectory, DanceOPD uses a single, low-noise query per sample, focusing on the most informative part of the generation process. The beauty of DanceOPD lies in its simplicity. The student model is updated using a plain velocity mean squared error, or MSE, objective. This objective naturally fits the task of matching deterministic velocity fields. What's more, this framework can also absorb operator-defined fields, such as classifier-free guidance, directly into the student model. This means that effects typically applied during inference can be learned and internalized during training, making the final model more efficient and capable of complex, guided generations without external intervention. DanceOPD demonstrates significant improvements across various tasks. In text-to-image and editing composition, it boosts editing performance by over 8% on gedit bench while maintaining or even improving base T2I quality. For local and global editing, it shows a 16% improvement over baselines. It also effectively absorbs realism-oriented fields, closing 85% of the student-to-teacher reward gap, and integrates classifier-free guidance, leading to better composition. The qualitative examples showcase its ability to perform diverse edits, from material changes to scene transformations, while preserving core image identity. While powerful, DanceOPD has limitations. It assumes that different capability sources expose compatible velocity fields, which holds true for models built on the same backbone, but might be challenging for disparate architectures. The current hard-routed approach relies on predefined task boundaries. Future work could explore more flexible routing, perhaps using a verifier model to dynamically assign capabilities based on prompt or desired edit success. This would allow for more ambiguous tasks or prompts requiring multiple capabilities simultaneously, pushing the boundaries of unified generative AI even further.